There is a thought experiment that a number of serious physicists refuse to discuss in public, not because it is absurd, but because they are quietly afraid it might be true. It begins with a simple machine, a trigger wired to a single subatomic particle. Pull it once, and in half of all possible outcomes, you die instantly. In the other half, nothing happens at all. Pull it again, and again, 1,000 times. By every ordinary measure of probability, you should be dead within seconds. And yet, the argument goes, from the inside, from behind your own eyes, you will never experience a single one of those deaths. You will only ever find yourself among the survivors. Not because you are lucky, because, in this reading of reality, there is always a version of you that lives, and your awareness has no choice but to follow it. This is quantum immortality, the disturbing corollary of a setup called quantum suicide. And it does not come from mysticism or fringe speculation. It follows, step by step, from one of the most respected frameworks in modern physics, the many worlds interpretation, the branching multiverse, formalized by cosmologist Max Tegmark. By the end of this video, you will understand where this idea came from, why the mathematics appears to permit it, what it would actually feel like to be a consciousness that cannot die, and why even the man who formalized it came to believe the comforting version is wrong. Keep one number in mind as we go: 1/2. We will return to what it costs. If you find value in explorations like this, consider subscribing to the channel, which helps these deep dives reach more curious minds. Now, let us begin. The story does not start with death. It starts with a cat that is neither alive nor dead, sealed inside a box. In 1935, the Austrian physicist Erwin Schrodinger described a scenario he intended as a criticism, a way of showing that something had gone wrong with the new physics of the very small. Place a cat in a sealed chamber. Add a single radioactive atom, a Geiger counter, and a vial of poison. If the atom decays, the counter triggers, the vial breaks, and the cat dies. If the atom does not decay, the cat lives. The behavior of that single atom is governed by quantum mechanics, and quantum mechanics does not say the atom has decayed or has not decayed. It says the atom exists in a superposition, a combination of both possibilities at once, until it is measured. Schrodinger's point was uncomfortable. If the atom is in a superposition of decayed and not decayed, then the counter is in a superposition of triggered and not triggered, and the cat is in a superposition of dead and alive. A living and dead cat is absurd. That was the entire purpose of the example. He was holding up a mirror to the theory and asking it to explain itself. To understand why this is more than wordplay, we need the central equation of quantum mechanics. It is called the Schrodinger equation, written down by Schrodinger himself in 1926. In speakable form, it reads I h bar d psi dt equals h hat psi. The symbol psi represents the quantum state, the complete description of a system. H hat is the Hamiltonian, the operator that encodes the system's energy. The h bar is the reduced Planck constant, the fundamental scale of the quantum world. And the equation describes how that state changes smoothly through time. The critical feature is this: the Schrodinger equation is deterministic and continuous. It contains no jumps, no collapse, no sudden choice between alive and dead. Left to itself, it evolves the superposition forward, faithfully, forever. So we are owed an account of where that single outcome comes from, of where the cat becomes definitely one thing. This is the measurement problem, and it is the oldest unsolved wound in quantum theory. The equations describe a smooth blend of possibilities. Our experience contains only sharp, single facts. Something has to bridge the two, and physics has never agreed on what. The dominant answer for most of the 20th century came from Niels Bohr and his circle in Copenhagen. The standard textbook view, the Copenhagen interpretation, holds that when a measurement occurs, the wave function collapses. The blend of possibilities snaps instantly into one, and which one it becomes is governed by the second great rule of quantum mechanics, the Born rule, formulated by the German physicist Max Born, also in 1926. The Born rule says that the probability of an outcome equals the square of the amplitude attached to it. In speakable form, probability equals the modulus squared of the amplitude. If the atom has a 50% amplitude weighting toward decay, you get a 50% chance of a dead cat. Hold on to that, because it matters more than it first appears. In the Copenhagen picture, the Born rule is postulated. It is added to the theory by hand as a separate assumption on top of the Schrodinger equation. The smooth equation tells you how the possibilities evolve. The Born rule, bolted on beside it, tells you the odds when one possibility becomes real. Nobody derives the second from the first. It is simply asserted because it works. We will return to this seam in the theory. It is the place where, much later, the entire structure will be tested. For now, notice what the collapse picture requires. It requires that measurement is special, that there is a line somewhere between the quantum world, where superpositions live, and the classical world, where cats are definitely alive or definitely dead. But the theory never tells you where that line is, never tells you what counts as a measurement, whether a Geiger counter, a human eye, or a conscious mind. The Copenhagen interpretation draws a boundary it cannot locate. And in 1957, a young graduate student at Princeton decided that the cleanest solution was to erase the boundary entirely. His name was Hugh Everett III. Born in 1930, an American, brilliant, blunt, and largely uninterested in the deference his elders expected, Working under the physicist John Wheeler, Everett asked a question of disarming simplicity. What if there is no collapse? What if the Schrodinger equation is the whole story, and it applies to everything, with no exceptions, no special role for measurement, no boundary at all? This is the heart of what became the many worlds interpretation. Tegmark would later compress Everett's idea to a single sentence, which he called the Everett postulate. All isolated systems evolve according to the Schrodinger equation. That is it. There is no second rule for measurement. The universe is one enormous quantum state, a single universal wave function, evolving smoothly and deterministically for all time. Without collapse, the fate of the cat takes a far stranger turn. Here, the mathematics becomes vivid. Consider the measurement written out. When an observer interacts with a particle that is in a superposition of two states, the Schrodinger equation does not pick one. It entangles them. Written symbolically, the unitary evolution takes a particle in a blend of up and down, together with a ready observer, and produces a sum of two terms. One term in which the particle is up and the observer has seen up, plus a second term in which the particle is down and the observer has seen down. Both terms are equally real. Both are contained in the one wave function. The observer has not collapsed anything. The observer has joined the superposition. There are now, in effect, two observers. One who saw the atom decay and the cat die, one who saw the atom hold and the cat live. Neither is more real than the other. Neither is a copy in the ordinary sense. They are two branches of a single, smoothly evolving reality, and each one feels, from the inside, like the only one. This is what people mean when they say the universe splits. Tegmark is careful to stress that Everett did not postulate a literal splitting. There is only ever one wave function. What creates the appearance of separate, non-interacting worlds is a physical process discovered later, called decoherence. Decoherence is the mechanism that makes many worlds livable as a theory, and it was identified by the German physicist Hans-Dieter Zeh in 1970. Zeh's insight was that no system is ever truly isolated. A cat, a counter, a person, a laboratory, all of it is constantly interacting with a vast environment of air molecules, photons, and thermal vibrations. The moment a superposition touches that environment, information about which branch is which leaks irreversibly into the surroundings. The branches stop being able to interfere with one another. As Tegmark phrased it, coherent quantum superpositions persist only as long as they remain secret from the rest of the world. Once the secret is out, once the environment has been touched, the branches are effectively sealed off from each other forever. They do not interact. They do not communicate. Each evolves on, blind to the others. This was not a comfortable idea when Zeh proposed it, He faced a hostile reaction from the Copenhagen establishment, which had spent 40 years treating the measurement boundary as settled. But decoherence has since become one of the most experimentally confirmed phenomena in physics. In 1996, the French physicist Serge Haroche measured decoherence directly, watching a controlled superposition of light inside a cavity lose its coherence in real time, in a paper published in Physical Review Letters. Haroche, along with the American physicist David Wineland, received the 2012 Nobel Prize in Physics for developing methods to measure and manipulate individual quantum systems. The mechanism is real. The branches, whatever else they are, genuinely stop talking to each other. Everett's theory, for all its elegance, was ignored for over a decade. His 1959 meeting with Niels Bohr in Copenhagen, intended to win the master over, was by all accounts a complete disaster. Bohr rejected the relative state formulation outright. Everett, discouraged, left academia entirely and went to work for the Pentagon, analyzing the mathematics of nuclear weapons targeting for the Weapons Systems Evaluation Group. The idea might have died there. It was rescued in 1970 by the physicist wheeler-dewitt, who wrote an article in Physics Today that popularized the theory and gave it the name that stuck: many worlds. It was DeWitt's phrasing, not Everett's, that captured the public imagination. The image of the universe ceaselessly splitting into countless copies. And here is where the thought experiment turns from cats to people. If there is no collapse, if every quantum outcome simply produces a branch in which it happened, then a measurement that determines whether you live or die does not kill you in any final sense. It splits you. In one branch, you are dead. In another, you are alive. And the version of you that is alive remembers everything up to that moment and continues, with no awareness whatsoever of the branch in which the story ended. Make the experiment deliberate, and you arrive at quantum suicide. The setup is precise. You build a machine, sometimes called the quantum gun, wired to a quantum random number generator, something genuinely quantum like the spin of a particle. The machine fires a lethal mechanism if the particle reads one way and does nothing if it reads the other. You place yourself in front of it and pull the trigger. Under the Copenhagen interpretation, you have a 50% chance of dying, full stop. After enough rounds, you are almost certainly dead. Under the many worlds interpretation, every pull splits the world. In half the branches, you die. In half, you live. But you can only ever experience the branches in which you survived, because in the others, there is no you left to experience anything. From the inside, you appear to be invulnerable. Max Tegmark, the Swedish-American cosmologist at MIT who formalized this argument in a 1998 paper, laid out 3 strict conditions for a genuine quantum suicide setup. First, the random number generator must be truly quantum, not merely some complicated but ordinary mechanical process. Second, the experimenter must be killed, or at least rendered unconscious, faster than they can become aware of the outcome. And third, the experiment must be virtually certain to kill, not merely to injure. Tegmark noted that most ordinary causes of death fail these conditions. As he put it, under normal circumstances, dying is not a binary thing where you are either alive or dead. What makes the quantum suicide argument work, he said, is that it forces an abrupt transition. Remember that phrase, abrupt transition. It will matter enormously later. The idea did not arrive fully formed, and it is worth tracing its lineage, because the careful original versions are quite different from the version that now circulates online. Among physicists, the cat's eye view of the experiment was introduced by Ewan Squires in 1986. It was published independently by the roboticist Hans Moravec in 1987, framed inside what he called a Doomsday device scenario about builders of a particle accelerator presented as observer relative survival rather than personal immortality. The Belgian logician Bruno Marchal arrived at a related idea in 1988, framed in terms of theoretical computer science, of consciousness persisting across computable structures. And the philosopher Hugh Price, writing in 1997, credited the survival idea to Zay himself, the same man who gave us Decoherence. Tegmark's contribution in 1998 was to make it rigorous, to spell out the conditions, to connect it explicitly to the many worlds mathematics. The modern popular version compresses all of this into 3 words: "You are immortal," and strips away every caveat the originators were careful to attach. We can put numbers on the divergence between the 2 pictures, and the numbers are stark. Consider the survival probability after repeated trials. In a collapse interpretation, your chance of being alive after n rounds is 1/2 raised to the power n. After 1 round, 50%. After 10, less than 1 in 1,000. After 20, less than 1 in 1,000,000. The curve plunges toward 0. In the many worlds interpretation, by contrast, there is always at least one branch in which you have survived every round, and that branch exists with certainty. 2 diverging lines on a graph, one falling to nothing, one holding stubbornly at the top. What does it mean that the same physical setup, described by the same equations, yields a death sentence under one interpretation and apparent immortality under another, with no experiment that anyone outside the box could ever perform to tell which is correct? That last point deserves emphasis, because it foreshadows a problem we will examine in full. Even a surviving experimenter cannot prove anything to anyone else. From outside the box, every observer always sees ordinary statistics. Roughly half the experimenters die. The survivor is convinced. No one else can be. The argument is, at best, self-verifying and never shareable. And one more seed to plant before we go deeper. When Tegmark conducted an informal poll of physicists at a conference in 1997, asking which interpretation of quantum mechanics they favoured, the results were not what the popular narrative suggests. Copenhagen led with 13 votes. Many worlds received 8. Bohmian mechanics and consistent histories received 4 each. Objective collapse received 1, and the largest group of all, 18, were undecided. The notion that the scientific community has quietly accepted the branching multiverse as established fact is, to put it plainly, overstated. Keep that in mind. We are not examining a consensus. We are examining one interpretation among several and tracing where its internal logic leads. To follow that logic, we have to understand how large the branching multiverse is claimed to be, and how it fits inside the broader landscape of parallel worlds that physicists discuss. Max Tegmark organized this landscape into 4 levels, and the distinction between them is the key to seeing what quantum immortality actually requires. The first level is the simplest. Space, if it is infinite, contains regions so far away that their light has never reached us and never will. Those regions obey the same physical laws as ours, but they contain different arrangements of matter. Given enough volume, somewhere out there, the same atoms fall into the same patterns, and a region identical to this one exists. This is the level 1 multiverse, and it requires nothing more exotic than an infinite space. The second level is bolder. In the theory of cosmic inflation, space gives rise to separate bubble universes, each potentially with different physical constants, different strengths of gravity and electromagnetism. This is the level 2 multiverse, the one most often invoked in discussions of fine-tuning. The third level is Everett's. The level 3 multiverse is the branching one, the worlds that split off with every quantum measurement. And here, Tegmark makes a remark that is easy to miss and impossible to forget once you have seen it. The only difference, he says, between level 1 and level 3 is where your duplicates reside. In the level 1 multiverse, your copies are far away in ordinary space. In the level 3 multiverse, they are right here, in the same space, but in branches of the wave function your branch can no longer touch. The distance between you and the version of you who made the opposite choice this morning is not measured in light years. It is measured in decoherence. They are, in a sense, closer than the next room and more unreachable than the edge of the observable universe. Then there is the fourth level, and this is where Tegmark's framework becomes genuinely radical. Level 4 multiverse rests on what he calls the mathematical universe hypothesis. The proposal has 2 parts. The first, the external reality hypothesis, simply says that physical reality exists independently of human observers. The second goes much further. It claims that physical reality is not merely described by mathematics, but that it is a mathematical structure through and through. And if our universe is one mathematical structure, Tegmark argues, then by a kind of mathematical democracy, all mathematical structures exist, each as real as any other, each its own universe. Under this view, the reason the equations work so unreasonably well is that there is nothing else underneath them. The equations are not a map of reality, they are the territory. This matters for our subject because it changes what survival means. In the level 3 picture, quantum immortality means your consciousness follows a branch in which your body keeps functioning. In the level 4 picture, survival becomes something stranger still. The persistence of a particular mathematical pattern, a structure complex enough to be conscious across the vast space of all possible structures. The theory of mind and the theory of everything fold into one another. We will return to whether mathematical existence and physical existence are really the same thing, because a great deal rides on that single, unproven assumption. For now, hold the framework in place and notice the crack that runs through its foundation. The entire quantum immortality argument rests on a quiet premise: that all branches are equal, that each outcome of each measurement spawns a world just as real, just as substantial as every other. But there is a body of work developed since the early 2000s that complicates this picture, and it comes from the physicist Wojciech Zurek at Los Alamos. Zurek's program is called Quantum Darwinism, proposed in 2003, and it builds directly on decoherence. The starting question is this: out of all the possible states a system could be in, why do we only ever observe certain ones, the definite positions, the definite outcomes, the pointer states, as Zurek calls them, named for the needle on a measuring instrument that always ends up pointing somewhere definite? His answer borrows the logic of natural selection. The environment does not merely destroy superpositions, it selects among them. Most quantum states are fragile and are immediately scrambled by contact with the environment. But a few special states are robust. They survive the interaction, and more than that, they imprint themselves redundantly, stamping copy after copy of their information into the surrounding world, into the photons and air molecules that then carry that information to every observer. Zurek calls this the environment as a witness. Reality becomes objective and shared precisely because the same record is broadcast in countless redundant copies, so that any number of observers can read it and agree. Zurek named the selection process Einselection, environment-induced super-selection. He helped prove a related and essential fact in 1982, the no-cloning theorem, which states that an arbitrary unknown quantum state cannot be perfectly copied. And in 2025, quantum Darwinism received an experimental demonstration on superconducting circuits, published in Science Advances, in which researchers watched a quantum system broadcast redundant records of itself into an engineered environment, exactly as the theory predicts. Now hold quantum Darwinism beside the quantum immortality argument and feel the friction. Quantum immortality needs every branch to be on equal footing, an unbroken democracy of worlds, so that there is always a branch in which you live and your consciousness can always find it. But quantum Darwinism says that not all states are equal, that the environment continuously selects which states are stable, which are recorded, which become part of objective reality at all. The egalitarian picture, the foundation of the entire immortality argument, has a visible crack running through it from within mainstream physics. We will widen that crack later. For now, simply mark it. Before we reach the deepest problem of all, it is worth stepping back to see how alone the many worlds interpretation is in producing this result, because the immortality argument works under no other reading of quantum mechanics. Place the major interpretations side by side, and ask each the same blunt question. You run the quantum suicide experiment many times. What happens to you? The Copenhagen interpretation answers first, and its answer is the ordinary one. The wave function collapses at each measurement. The Born rule sets the odds, and after enough rounds, you are, with overwhelming probability, simply dead. There is no surviving branch to inhabit, because there are no branches at all, only the single outcome, that collapse selected. Bohmian mechanics, the pilot wave theory first sketched by the French physicist Louis de Broglie in 1927 and developed by the American physicist David Bohm in 1952, reaches the same verdict by a completely different route. In this picture, there is only one world. Particles have definite positions at all times, carried along by the wave through what is called the guidance equation, which fixes each particle's velocity from the shape of the wave function. Nothing branches. As the computer scientist Scott Aaronson put it, at the end of a Schrodinger's cat experiment, there are exactly as many cats as there were at the beginning, namely one, either alive or dead. Run quantum suicide in a Bohmian world and you die once for real. Objective collapse theories give the same answer a third way. The best known is the GRW model, named for the physicists Girardi, Rimini and Weber, and proposed in 1986. And it modifies the Schrodinger equation itself. Each particle carries a tiny probability per unit time of spontaneously localizing, of jumping to a definite position. For a single particle, this almost never happens. But because the rate scales with the number of particles, a macroscopic object, with its uncountable particles, collapses to one definite state almost instantly. In the GRW picture, collapse is a real, physical, stochastic event, not an interpretive gloss. The cat becomes genuinely alive or genuinely dead within a fraction of a second, and the experimenter genuinely dies. It is worth noting that the philosopher David Lewis, near the end of his life, tentatively favoured this objective collapse picture over many worlds, precisely because of where the alternative seemed to lead. Lay the four answers in a row. Copenhagen, you die. Bohm, you die. Objective collapse, you die. Only the many worlds interpretation produces a surviving you, and only because it alone refuses to let any outcome fail to happen. What does it mean that the entire architecture of quantum immortality stands or falls on the single most contested choice in the foundations of physics, the one choice that 3 of the 4 leading interpretations reject outright? This is also the place to feel the sheer scale of what the branching picture proposes, because the splitting is not occasional, it is ceaseless and astronomically prolific. Tegmark offers an illustrative calculation. A pencil balanced perfectly on its tip is a quantum system poised between directions, and it would topple into a superposition of falling every possible way within about 30 seconds. Now count the branchings. For n binary quantum events, the wave function contains 2 raised to the power n distinct terms. After only about 300 such events, you have 2 to the 300th power, which is roughly 10 to the 90th, a figure comparable to the number of atoms in the entire observable universe. And 300 quantum events is nothing. They occur in unimaginable numbers every instant, in every object, in your own body as you sit here. If the picture is literally true, the number of branches generated since this sentence began is past any name we have for large. Physicists track the structure of all this branching with a tool borrowed from information theory, the von Neumann entropy. In speakable form, it reads S equals minus the trace of rho log rho. The symbol rho is the density matrix, the mathematical object that encodes a quantum system's state, including its entanglement with the environment. The von Neumann entropy measures how thoroughly a system has decohered, how completely it has entangled with its surroundings and separated into effectively independent branches. It is the bookkeeping of branching, the ledger that records how a clean superposition becomes a forest of non-interacting worlds. It is precise, it is calculable, and it is mainstream physics. What it does not tell you, what no equation in the framework tells you, is which branch carries your awareness, or what your awareness even is. There is a sharper version of the measurement puzzle that bears directly on the question of the self, and it is a close relative of Schrödinger's cat, known as Wigner's friend. Picture a scientist, the friend, who performs a quantum measurement inside a sealed laboratory and records a definite result. Now picture Wigner standing outside, who has not opened the lab. From Wigner's vantage, the laboratory, the apparatus, and the friend together are still one large quantum system in superposition, the friend having registered both outcomes at once. Inside, a definite fact; outside, no definite fact at all. Two observers, one reality, and no agreed answer to the simple question of what actually happened. Wigner's friend takes the measurement problem and drives it directly into the seat of consciousness, and it sets up the exact difficulty the immortality argument will founder on. If even what an observer has definitely experienced can depend on who is asking, what precisely is the self that is supposed to survive every branching forever? It would be convenient if decoherence quietly dissolved all of this, and it is sometimes presented as if it does. But honesty requires a caveat that the founders of the field themselves insist upon. Decoherence explains, with great success, why we never see superpositions, why the branches stop interfering, why the world looks reassuringly classical. It does not, on its own, explain why one outcome rather than another is the one you experience. Its own architects are explicit that decoherence alone does not fully solve the measurement problem. It tells you the branches separate. It does not tell you why you find yourself on this one. Hold that admission. It will matter a great deal when we ask whether physics can account for the observer at all. And the strangeness reaches outward, into cosmology, through a family of arguments that share quantum immortality's most dangerous move. The move of reasoning about all of reality from the bare fact of one's own existence as an observer. One such relative is the Boltzmann brain. In a universe vast enough, or old enough, random fluctuations should occasionally, by sheer chance, assemble a fully formed conscious mind, complete with false memories, that flickers into being and dissolves. The disturbing question it raises is statistical. In some cosmological models, such randomly fluctuated observers would vastly outnumber ordinary, evolved ones like us. So, on what grounds do you trust that you are a real person with a real past, rather than a momentary fluctuation that congealed an instant ago? Another relative is the Doomsday argument, which uses your position in the sequence of all humans who will ever live to draw conclusions about how long our species has left. Each of these, like quantum immortality, treats the observer as a sample to reason from, and each runs into the same treacherous water when it tries to turn the existence of a witness into a conclusion about the world. We will see shortly that this very move, anthropic reasoning, observer-based reasoning, is precisely what Tegmark eventually reaches for in order to diffuse his own creation. What does it mean that the same style of argument can be used to prove you are immortal, to suggest you are a hallucination, and to forecast the end of humankind? This brings us to the deepest technical problem in the whole structure, and it is the problem of probability itself. It is usually called the measure problem, and to feel its force, you must see exactly what the many worlds interpretation gave up. Recall that in the Copenhagen picture, the Born rule, probability equals amplitude squared, was added by hand. It was a postulate. The great selling point of the many worlds interpretation was that it would need no such postulate, that it would contain only the smooth Schrodinger equation and nothing else. But that elegance creates an immediate puzzle. If every outcome happens in some branch with certainty, then what could probability even mean? Consider a measurement with two outcomes, one assigned a 90% amplitude weighting and the other 10%. In the real world, we observe the first outcome about 9 times in 10. That is the Born rule, confirmed in laboratory after laboratory for a century. But in the many worlds picture, both outcomes simply happen. There is one branch where you saw the first result, and one branch where you saw the second. One branch and one branch. By naive counting, that is 50-50, not 90-10. So the Born rule probabilities have to come from somewhere, and it is far from clear why the world should be weighted at all if each is a fully real branch. Everett himself had a name for the troublesome branches in which the usual statistics fail to hold. He called them maverick branches, and the whole challenge is to explain why we do not find ourselves in one. The defenders of many worlds have a sophisticated response, developed primarily by the physicist David Deutsch in 1999 and the philosopher David Wallace, and later by Sean Carroll. It is a decision-theoretic and self-locating argument. The idea is that immediately after a branching event, but before you have looked at the result, there is a genuine sense in which you do not know which branch you are on. You are uncertain about your own location among the branches. Carroll and his colleague Charles Sebans, in work around 2013 and 2014, argued that if you reason carefully about this self-locating uncertainty, assigning rational credences to which branch you might be in, the weights you are forced to adopt are exactly the Born rule weights, amplitude squared. The probabilities on this view are not built into the physics, they emerge from the rational expectations of observers embedded inside it. It is an ingenious argument, and whether it actually succeeds is, in the words of the Stanford Encyclopedia of Philosophy, a highly controversial question. We will weigh the criticisms in the final part of this exploration. For now, present it fairly, as its authors intended, and notice only this. The probabilities that the entire quantum immortality argument depends upon, the one half we were asked to remember, are not a clean output of the theory. They are the subject of a decades-long, unresolved dispute among the theory's own supporters. What does it mean that the single number at the center of the argument has to be argued for, rather than simply read off the equations? There is another dimension to all of this that reframes the question of survival entirely, and it comes from relativity rather than quantum mechanics. It is the block universe. In Einstein's relativity, time is not a universal river flowing for everyone at the same rate. Past, present and future are woven together into a single four-dimensional structure, space-time. And within that structure there is, as physicists like to say, nothing special about now. Every moment exists fixed as a coordinate. Tegmark put it memorably. Time, he said, is the fourth dimension, and the passage of time is an illusion. If life were a movie, physical reality would be the entire DVD. Future and past frames exist just as much as the present one. Your whole life, from first breath to last, is a fixed shape inside the block, a world tube, a four-dimensional thread. Nothing about it is created or destroyed. The only thing that moves is your awareness, which, in one striking phrase, crawls along the world line, lighting up each moment in turn and producing the illusion that things are happening. Marry the block universe to the branching multiverse, and quantum immortality takes on an even colder character. The branches may not be events that happen in time at all. They may be co-eternal structures, all of them simply there, fixed in the timeless block. And what we experience as surviving one round after another is only consciousness crawling along one particular thread through a frozen, four-dimensional lattice of every possible thread. There is no escape because there is no flow to escape from. There is only the structure and your awareness tracing its path. Physics has a candidate equation for this timeless reality, and it is one of the strangest in all of science. It is called the Wheeler-DeWitt equation, written down around 1967 by John Wheeler, Everett's old advisor, and Bryce DeWitt, the man who named many worlds. The equation is an attempt to apply quantum mechanics to the entire universe, including gravity. Time variable at all. It describes a universe that does not evolve, that simply is a single frozen wave function. Some physicists have written, with evident discomfort, that the equation suggests nothing at all happens in the universe. This is called the problem of time, and it remains unsolved. What does it mean that our best candidate for the fundamental equation of the cosmos contains no time, while every conscious being who has ever lived has experienced nothing but its passage? Now let us return, as promised, to the cost. If quantum immortality were true, the lived reality of it would be nothing like the comfortable story. The popular version imagines endless youthful survival, a comfortable invincibility. The careful version is a horror. The philosopher David Lewis devoted one of his last public lectures to this, delivered in 2001, only months before his own death, under the title, "How Many Lives Has Schrodinger's Cat?" Lewis pointed out a corollary that the optimistic account ignores. Many worlds' quantum immortality guarantees that you survive. It does not guarantee that you survive intact. Think of every way you could survive a catastrophe. For each branch in which you walk away unharmed, there are vastly more branches in which you survive but maimed, burned, brain damaged, kept barely alive. There are enormously more physical configurations corresponding to barely alive and grievously injured than to perfectly healthy, simply because there are more ways to be broken than to be whole. So, if your consciousness is condemned to follow some surviving branch, the overwhelming weight of those branches points not toward health, but toward deterioration. You would survive, and survive, and survive, accumulating damage that never quite kills you, forever just short of death. This is sometimes called the Tithonus corollary, after the figure in Greek myth who was granted immortality but not eternal youth, and who withered without end. Survival is guaranteed, mercy is not. The philosopher István Aranyossi explored the alternatives in 2012, including a grimmer one still: an eternal existence spent almost entirely unconscious, punctuated only by brief amnesiac flickers of awareness, each one isolated, each one forgetting the last. And the cosmologist Anthony Aguirre noted a consequence that borders on the unbearable. If loss of consciousness were a genuinely binary event, the quantum immortality effect would prevent you from ever subjectively falling asleep, ever undergoing anesthesia, ever losing awareness at all, because your consciousness would always have to find a branch in which it persists. Aguirre's own verdict on letting any of this guide your actions is blunt. It would be foolish and selfish in the extreme, he wrote, to let this possibility guide one's actions in any life and death question. There is also the question of whether the surviving version is even you. And this is where the no-cloning theorem and the philosophy of identity collide. The branches contain beings continuous with your past, who remember being you. But the British philosopher Derek Parfit argued in his 1984 work, Reasons and Persons, that personal identity is not the deep, all-or-nothing fact we imagine. What matters, he said, is only psychological continuity and connectedness, what he called relation R, and there is no further fact of the matter beyond that. If Parfit is right, the question of whether the survivor is really you may have no determinate answer at all. And the no cloning theorem sharpens the knife. An arbitrary, unknown quantum state cannot be perfectly duplicated, which complicates the naive image of identical copies of you populating the branches. Keep this tension in view, because it will turn out to undermine the whole argument from within. The immortality argument needs a single, persisting self that the branches preserve. The physics and philosophy it rides on may deny that such a self exists at all. Finally, follow the immortal observer all the way to the end, not of a life, but of the cosmos, because this is where the dread becomes physical. If consciousness truly cannot terminate, it does not simply outlive the body, it outlives everything. Run the clock forward. The stars burn out. If protons decay, all ordinary matter dissolves on a timescale of around 10 to the 40th power years. The black holes themselves evaporate, the last of them gone by perhaps 10 to the 100th power years. A span the cosmologist Katie Mack has noted is on the order of a googol of years before heat death truly gets rolling. And there are darker possibilities than slow cold. If dark energy behaves in a certain extreme way, a phantom form, the universe could end in a big rip. In one worked example by Caldwell, Kamiankowski and Weinberg in 2003, the tearing apart of galaxies, then solar systems, then atoms themselves, roughly 22 billion years from now. Or the vacuum itself could be unstable. A 2018 analysis using the Standard Model placed the lifetime of our vacuum somewhere between 10 to the 65th and 10 to the 725th power years. A bubble of true vacuum that, once nucleated, would expand outward at the speed of light, very nearly 300,000 kilometers per second, rewriting the laws of physics inside it. An immortal consciousness, on the quantum immortality argument, would be forced to experience the approach of each of these ends, and then to find the one branch, however vanishingly weighted, in which it somehow continues past them. Not peace, not rest, just the next branch and the next, into a darkness with no floor. I said earlier we are tracing the internal logic of one interpretation. We have now followed it from a cat in a box to a consciousness that cannot stop, across 4 levels of multiverse, through the unsolved problem of probability and the frozen equation of the universe. The branching picture at the root of all this, the foundational claim that every choice spawns an equally real world, is a subject deep enough to deserve its own full treatment, and I have explored it on its own terms elsewhere. But here, our concern is the corollary, the immortality, and the assumptions it smuggles in. We have been fair. We have presented the strongest case. Now the evidence goes under examination. Let us begin the examination where it does the most damage, with the man who built the argument in the first place. Because the single most important fact about quantum immortality is one the popular accounts almost never mention. Max Tegmark, the cosmologist who formalized the whole thing in 1998, does not believe the popular version. He walked it back. Recall the third of his own conditions for a genuine quantum suicide setup. The death must be abrupt, faster than the experimenter can register the outcome. Tegmark came to see that this condition almost never holds, and that the failure is not a technicality. It is fatal to the conclusion. In his 2014 book, Our Mathematical Universe, and in an interview recorded a decade earlier, he spelled out why. Dying, he observed, is not a binary event. It is a progressive process, a continuum of states of decreasing consciousness. And once you see that, the immortality argument dissolves. In his own words, the fading of consciousness is a continuous process. Although I cannot experience a world line in which I am altogether absent, I can enter one in which my speed of thought is diminishing, my memories and other faculties fading. I am confident, he said, that even if he cannot die all at once, he can gently fade away. Read that carefully, because it is the architect of the theory taking his own building apart. The whole trick of quantum immortality depended on death being a switch, a clean jump from fully alive to instantly gone, with your consciousness forced to leap to the surviving branch. But consciousness does not switch off. It dims. And along the overwhelming majority of branches, it dims toward zero. Tegmark now holds that an experimenter should expect only a normal probability of survival, not immortality, because the surviving branch carries a vanishingly small measure, and, by the anthropic principle, you are far less likely to find yourself in a world of tiny measure than in an ordinary one. The strongest popular version of this idea is rejected by the very person who gave it its rigorous form. Consider what kind of move this is in an argument. When the building inspector who certified the foundation is the one standing outside telling you the structure is unsound, you do not need to be an engineer to take the warning seriously. It is not a rival who is raising the objection, it is the author. And what does it mean that the most shared, most frightening form of quantum immortality survives in the popular imagination only by ignoring the published retraction of the man who created it? But suppose we set Tegmark's retraction aside and grant the argument its best case anyway. It still cannot stand because it rests on a number it is not entitled to. This is the measure problem, and it is the hinge on which everything turns. The entire inference from "there is always a surviving branch" to "you will experience survival" requires that probabilities make sense in the branching picture. And they do not without help. Walk through the logic slowly, because it is the cleanest demolition available, and it requires no theology at all, only arithmetic. The many worlds interpretation was sold as the lean theory, the one that needs only the Schrodinger equation and discards the Born rule postulate. But strip out the Born rule, and you cannot recover the probabilities of ordinary quantum mechanics. Every outcome happens in some branch. Counting branches gives you even odds, 50-50, no matter what the amplitudes say. To get back the 90-10, the 1 in a million, the actual numbers confirmed in a century of experiments, the theory's defenders must add something: a decision-theoretic axiom, a self-locating credence rule, an additional assumption about how rational observers should bet. In other words, to recover the very probabilities it claimed to derive for free, the lean theory has to put a postulate back in. The elegance was an accounting trick. The bill comes due at the measure problem. And the theory's own experts admit the bill is unpaid. Listen to Adrian Kent, the Cambridge physicist who has examined many worlds more carefully than almost anyone. No known version of the theory, he writes, unadorned by extra ad hoc postulates, can account for the appearance of probabilities and explain why our evolutionary history appears to be born rule typical. Listen to the physicist Sabine Hossenfelder, who states it without hedging. The many worlds interpretation does not solve the measurement problem, and therefore it is equally troubled as all other interpretations of quantum mechanics. Listen to the physicist Stephen Su, who argues that the decision-theoretic derivations do not resolve the problem because they are circular. They assume in advance that the observer occupies a non-maverick branch, which is the very thing they were supposed to prove. Even David Wallace, perhaps the most able defender the interpretation has, concedes that his own objections to quantum immortality fall short of being a knockdown refutation, which is a careful philosopher's way of admitting the matter is unsettled at its core. So consider what quantum immortality actually is, stated precisely. It is a corollary of an interpretation of quantum mechanics drawn through a probability rule that the interpretation cannot justify, applied to a notion of personal survival that, as we will see, the same interpretation cannot support. It is not a prediction of physics. It is an interpretation, layered on an interpretation, leaning on an assumption, balanced on a definition. What does it mean that an idea presented to millions as a consequence of hard science turns out, on inspection, to be a tower of unproven premises with the equations only at the very bottom? This is the point at which the topic stops being merely a curiosity and starts making a larger claim, the claim that requires the most careful examination. Because in its strongest cultural form, the branching multiverse is offered as something more than physics. It is offered as a worldview. And that worldview can be stated in 3 propositions, each of which has been presented by various advocates as the lesson of all this. The first, that no creator is needed because everything that can happen simply happens automatically, with no one to choose or to cause. The second, that consciousness is merely matter or information, and the self is an illusion that splits freely with every branching, nothing more than a pattern. And the third, that purpose and meaning do not exist, because the passage of time itself is an illusion, and nothing truly comes to be. Let us take these one at a time, fairly stated and honestly tested. Consider the first claim, that the multiverse removes the need for any cause behind the cosmos. The reasoning goes like this. If every possibility is automatically realized in some branch or some structure, then there is no need to explain why this particular universe exists with these particular features. It is not special. It is just one of everything, and everything exists. In the Level 4 version, This reaches its furthest extent. All mathematical structures exist, so the existence of ours requires no explanation beyond the bare consistency of its mathematics. Proponents point to the elegance of unitary quantum mechanics and to what Tegmark calls mathematical democracy. Now examine the claim. The first thing to notice is that it has no evidence, and by its own nature can have none. No other branch has ever been observed, measured, or detected, and after decoherence, none ever can be, because the branches no longer interact. No level 2 bubble universe has been seen. No level 4 alternative mathematical structure has been or could be instrumented. The proposal is unfalsifiable in the strict sense. There is no possible observation that could count against it. By the ordinary standards of the scientific method, an entity that explains everything and forbids nothing is not a scientific hypothesis. It is a philosophical posture wearing the clothing of physics. And here the argument can be turned around on those who make it. The standard accusation levelled at theists is the charge of the god of the gaps, of invoking an unseen cause to paper over what science has not yet explained. But what is an infinite, undetectable ensemble of universes, invented for the express purpose of removing the need for a cause, if not a naturalism of the gaps? An unobservable, posited specifically to avoid a conclusion the evidence was pointing toward. The multiverse, deployed this way, is not a discovery. It is an escape hatch. And it has the curious property that it can never be checked. This is most visible in how the multiverse is wielded against the fine-tuning of the cosmos. The physical constants of our universe sit within astonishingly narrow ranges that permit stars, chemistry, and life. Shift several of them by a hair, and nothing of interest could form. Faced with that precision, the everything exists worldview answers that, with infinitely many universes sporting random constants, we simply happen to inhabit one of the rare hospitable ones, and no intention is required. But notice the shape of the reply. To avoid the conclusion that the settings were chosen, it conjures an unbounded, unobservable machinery of universes, whose existence is asserted precisely because it would erase the need for a chooser. It is a vast metaphysical purchase made specifically to pay down a single bill. And it still leaves the deeper invoice unpaid, because a constant randomizing mechanism that reliably produces universes is itself a finely structured thing that would demand its own explanation. You do not dissolve the appearance of design by proposing an unseen factory to manufacture the appearance away. You relocate the design into the factory. When I first worked through this argument carefully, the thing that unsettled me was not the dread of a consciousness that cannot die. It was how much unproven philosophy had been quietly folded into something presented to the public as the cutting edge of physics. The equations are real. The interpretation is a choice. And the worldview hung upon the interpretation is a third thing again, asserted with a confidence the layers beneath it do not earn. That is the part that stays with me. Not the fear, but the substitution of certainty for evidence. Before I go on, consider something honestly and take a moment with it. If the version of you that survives every branching is, on the theory's own terms, a freshly instantiated copy that merely remembers being you, then ask yourself plainly what it was you were hoping would be preserved. The atoms? The memories? Or the single continuous witness behind your eyes? The one the theory cannot locate and cannot guarantee. What would you actually conclude from this evidence if you followed it where it leads, rather than where you wished it to go? There is a sharper problem still, and it comes from within the field, from the cosmologist Alexander Vilenkin, who is no friend of theism. Vilenkin pointed out that the level 4 idea, that all mathematical structures exist, makes a prediction it cannot survive. The number of mathematical structures grows explosively with their complexity. The overwhelming majority of them are, in his words, horrendously large and cumbersome. So, if we were a random structure drawn from the space of all structures, we should expect to find ourselves in something baroque and tangled almost beyond description. Instead, he notes, the theories that describe our world are marked by beauty and simplicity. That is in direct conflict with a prediction. A typical member of the ensemble looks nothing like the elegant, lawful, intelligible cosmos we actually inhabit. The orderliness of our universe is not what the everything exists hypothesis predicts. It is what it struggles most to explain. And even Tegmark concedes the foundation is cracked. He has acknowledged that the level 4 hypothesis runs into the problem of Gödel undecidability, that mathematics itself contains truths that cannot be derived, structures that cannot be computed, and that this forced him to retreat to a more restricted version he calls the computable universe hypothesis. The grand claim that mathematical existence simply equals physical existence turns out to rest on an assumption its own author has had to qualify and shrink. So strip the rhetoric away and ask the question the everything exists worldview cannot answer. Why is there something rather than nothing? Suppose, for the sake of argument, every branch and every bubble and every mathematical structure does exist. You have not answered the question. You have multiplied it. Now you must explain why the entire ensemble exists rather than no ensemble at all, and why mathematical structures should be physically instantiated, should burn with actual existence, rather than remaining what mathematics has always been, a realm of abstract possibility. A blueprint does not build the house. A description of a fire does not give off heat. The proponents of mathematical democracy assert that the structures simply are, eternally and without cause. But notice what that is. It is the claim that something has always existed, uncaused, necessary, the ground of everything else. That is not the elimination of an eternal first cause. That is an eternal first cause renamed and assumed to be an unconscious abstraction rather than an intelligent one. And that substitution is exactly where the reasoning fails. Because unconscious abstractions do not do the one thing this cosmos visibly required. They do not choose. A mathematical structure has no power to confer existence on itself. The number 7 does not reach out of the realm of arithmetic and become a stone. For a possibility to become an actuality, something must select it and give it being. The everything exists picture tries to avoid that selection by making everything actual. But it cannot escape the prior question of why there is actuality at all, why the lights are on, why the equations are not merely true but obeyed. Something must always have existed. The only question is whether that something is an unconscious structure with no power to choose, or an intelligent cause with power, knowledge, and will. The order, the simplicity, the sheer fine-tuned intelligibility of what we observe, the very fact that reality is written in mathematics a mind can read, points away from blind abstraction and toward intention. What does it mean that the universe is comprehensible at all? That it yields to equations? That a structure built of unconscious matter should be transparent to thought? Consider now the second claim, which lies even closer to the heart of quantum immortality, because the whole argument depends on it. It is the claim that consciousness is merely matter or information, and that the self is an illusion that can split, copy, and continue with no remainder. The reasoning, often borrowed from Derek Parfit, holds that there is no deep fact of personal identity, no further fact beyond physical and psychological continuity. So a branching self is no more puzzling than any other persistence through time. You are a pattern. Patterns can fork. Here the argument does something quietly self-destructive, and to see it, we only need to take it at its word. Quantum immortality is the claim that you will never experience your own death, that your subjective awareness will always continue. But that promise requires a genuine subject, a you, an experiencer who persists to do the experiencing. Now pair that with the premise the same worldview insists upon, that the self is only a pattern, an illusion, with no further fact to anchor it. If there is no real, persisting self, then there is no one for whom survival is guaranteed. The branch that lives contains a being who resembles you and remembers being you. But, on the theory's own terms, that being is, at best, a copy, a freshly instantiated pattern, not the continuation of a single thread of awareness. The comfort offered that you will go on evaporates, because the theory has already dissolved the you that was supposed to do the going on. The argument eats its own premise. It needs a self robust enough to be immortal and a self too thin to be real in the same breath. And the physics tightens this further. Recall the no-cloning theorem, which forbids the perfect copying of an arbitrary unknown quantum state. The casual image of identical copies of you, distributed neatly across the branches, is not even clean within the mathematics. What persists is continuity, resemblance, memory, not duplication of a deep self, because the framework provides no deep self to duplicate. Philip Ball, the British science writer, put the consequence starkly. The many worlds interpretation, he argues, eliminates any coherent notion of what we can experience, or have experienced, or are experiencing right now, because it becomes logically impossible to connect the perceptions of the person before a branching to the person after it. The theory that was supposed to guarantee the continuity of your experience turns out to make the continuity of experience incoherent. Step back, and the deeper point comes into view, the one that no version of materialism has answered. The quantum immortality argument simply assumes that consciousness will follow a branch, that subjective experience attaches itself to surviving matter and rides along. But how does any arrangement of unconscious particles produce subjective experience in the first place? This is the hard problem of consciousness, and it remains entirely unsolved. Neuroscience can correlate brain states with mental states. It can tell you which regions light up when you feel fear or see red. It cannot tell you why there is something it is like to feel fear or see red at all. Why the lights of awareness are on inside the skull rather than the machinery simply running in the dark. Atoms have no inner life. Molecules have no point of view. No one has ever shown how to get a subject, a first-person witness, out of objects that have no perspective whatsoever. And quantum immortality does not merely fail to solve this. It builds its entire edifice on top of it, presupposing that consciousness persists, continues, and transfers, without ever explaining how unconscious matter became conscious in the first place. You cannot promise a mind eternal survival when you cannot account for the existence of the mind at all. What does it mean that the most confident claims about the fate of consciousness are made by a framework that cannot say what consciousness is? If consciousness were merely a byproduct of particles, we could perhaps speak of patterns forking and copies continuing. But the existence of a unified first-person awareness, the I that observes thoughts and persists through a life, is precisely what unconscious matter cannot supply. Arrangements of mindless particles do not become minds by being arranged more cleverly. Something more than matter is present in the one being in the cosmos who can sit and wonder whether it is immortal. And a thing that points beyond matter points toward a cause that is itself more than matter. Consider the third claim, gentler in tone, but no less consequential, that purpose and meaning do not exist because the passage of time is an illusion, and nothing genuinely comes to be. The block universe, recall, presents your life as a fixed world tube in a four-dimensional structure. Every moment already there, your awareness merely crawling along it. From this, some conclude that becoming is unreal, that choice is theatre, that meaning is a story we tell about a structure that simply sits, eternal and indifferent. But examine what has actually been established versus what has been smuggled in. That space-time can be modeled as a four-dimensional whole is a feature of relativity, a profoundly successful description. That this entails the unreality of all meaning is not physics at all. It is a metaphysical interpretation laid on top of the physics. And the leap from the structure exists timelessly to therefore nothing matters is pure assertion. A musical score exists all at once on the page, every note fixed, and that takes nothing away from the meaning of the music. A life that exists as a whole in the block is not thereby drained of significance. If anything, a fixed and permanent world tube is the opposite of meaningless, a life that can never be erased. The eternalist picture, even if true, says nothing whatever about whether existence has purpose. That is a question physics is not equipped to ask. And this is the recurring pattern in all three claims, the deepest lesson of the entire examination. Science describes how, it cannot pronounce on why. The Schrodinger equation describes how the quantum state evolves. It does not say why there is a state, or why the equation holds, or why anything obeys it. The block universe describes the geometry of space-time. It does not say why space-time exists, or why it is ordered rather than chaotic. The wheeler-dewitt equation, that frozen h hat psi equals 0, describes a timeless wave function, and, in doing so, cannot even account for the flow of time that every conscious being experiences without exception. At every level, the equations describe the operation of a reality whose existence they presuppose and cannot explain. To take a description of how something behaves and treat it as an explanation of why it exists is one of the oldest confusions in thought, and the grandest claims of the branching multiverse rest squarely upon it. So where does the evidence actually lead when we follow it honestly rather than where a prior commitment to materialism insists it must go? It leads to something with attributes the everything exists worldview keeps trying and failing to do without. The cosmos had a beginning. It is governed by laws of extraordinary precision and elegance. It is intelligible, written in a mathematics that a mind can read. It contains conscious observers, first-person witnesses who can comprehend it. Unconscious matter produces none of these on its own. Not existence, not order, not intelligibility, not mind. Each one points to a cause that possesses what the effects display. Power, to confer existence where there was none. Knowledge, to specify laws of such precision. Will, to choose this reality out of the infinity of possibilities rather than leaving everything as bare, abstract possibility forever. These are not the properties of an equation or an ensemble. They are the properties of an intelligent cause. The branching multiverse, in the end, does not eliminate that cause. It elaborately and unfalsifiably renames it, and hopes no one asks why the ensemble exists, why mathematics burns with being, why there is a witness present to ask the question at all. There is a human weight to this, and it would be dishonest to end the prosecution without feeling it. Hugh Everett, the originator of all of this, believed his theory guaranteed his own immortality. His biographers record that he held this conviction privately and firmly, that his consciousness would always follow the branch that did not lead to death. He was a committed atheist. He left physics for weapons analysis, and he lived hard. He died of a heart attack in 1982, at 51, after years of obesity, heavy drinking, and chain smoking. He believed he could not truly die, and he died young. And there is a darker grief still. In 1996, his daughter, Liz, took her own life. And in her note, she wrote that she was going to join her father in another universe. This is what it looks like when a corollary built on unproven premises is mistaken for a promise. It does not stay on the page. The mainstream physicists who study this idea are unanimous on one practical point, and they state it with unusual bluntness. Lev Weidmann, the large measures of the worlds with dead successors are a good reason not to play. David Deutsch, himself a champion of many worlds, on the survival reasoning, it requires an additional assumption, and my guess is that the assumption is false. Anthony Aguirre, it would be foolish and selfish in the extreme to let this possibility guide one's actions. The people who understand the theory best are begging you not to believe the frightening story told in its name. What does it mean that an idea offered as the bravest, most rigorous frontier of physics turns, when examined, into a warning, a grief, and a confession that its central inference cannot be justified? It means we have been looking at the wrong source of comfort. There is no consolation in a branching multiverse where, at best, a degraded copy of you is condemned to deteriorate without end, and where, at worst, the equations cannot even tell you that the copy is you. The longing behind quantum immortality, the hope that consciousness does not simply end, is real and ancient and very nearly universal. But it is not answered by an unfalsifiable ensemble of worlds. It is the kind of question that physics, by its own admission, was never built to answer, the kind that points beyond the equations to the one who wrote them. Let me bring this exploration to a close. We began with a cat in a sealed box, neither alive nor dead, and Schrödinger's quiet warning that something in the new physics did not add up. We followed Hugh Everett's radical solution, the removal of collapse and the birth of the many worlds interpretation, a single universal wave function branching endlessly through decoherence. We watched that branching turned inward into quantum suicide and its terrible corollary, quantum immortality, the claim that your consciousness can never experience its own death. We climbed through Max Tegmark's 4 levels of multiverse up to the mathematical democracy of level 4. We met the measure problem, the unpaid debt at the center of the theory, and the frozen, timeless equation of Wheeler and DeWitt, where nothing happens at all. And when we examined the immortality argument honestly, it came apart in our hands. Its own author retracted the popular version. Its central probability cannot be derived from its own equations. The self it promises to preserve is denied by the very framework it depends on. The consciousness it promises to carry forward is something that framework cannot even explain. And the worldview built upon it, that no cause is needed because everything simply exists, turns out to be an unobservable posited to avoid a conclusion, a naturalism of the gaps that multiplies the mystery instead of solving it. The evidence, followed without flinching, does not point to a cosmos that made itself out of nothing and needs no one. It points to power, to knowledge, and to will. It points to an intelligent cause. If you found value in this exploration, consider subscribing. It helps these deep dives reach more curious minds. And if one question has stayed with you through all of this, let it be the one beneath the immortality, the branching itself, the claim that every choice you make spawns a world just as real as this one, where the road you did not take is being walked by someone who remembers being you. I have followed that idea much further on its own terms, what it would mean for every version of your life to be equally real. You will find where, on the end screen and in the description below. Everett believed he was immortal, bound at every branching to follow the path that did not end. He was wrong about the comfort and wrong about the cost, and in the end, he was simply gone, mourned in this single world by the people who loved him. The mathematics is elegant. The price, if you take it literally, is a universe with no exit and no mercy. The truer reading is older and quieter, that a life is not an accident of branching amplitudes, but a thing brought deliberately into being, held in existence by the same will that lit the equations and set them running. Rest well tonight in this one world, the only branch your awareness was ever given, and consider who it was given by. Good night.